Hello, everyone. Welcome back to Coding Every Day. Today is February 2nd, day, day 18. It's 1:02 p.m. on a Sunday today. And I'm going to try another tree problem today. I've never looked at this one, so let's check it out. Count good nodes in binary tree. So recently I feel like I've been doing decent with the tree problems. So I'm looking forward to seeing this one. Okay. So it looks like we have to count the amount of good nodes, and good nodes are defined as if the path from the root of the tree to the node x contains no nodes with a value greater than the value of node x. So essentially it's like the local max, it looks like. So let's look at some examples here. So the root will always be a good node because there is no path greater than it from the root. 1 and 1 are both not good nodes because 2 is greater than that. And then 3 is the greatest so far on 2, 1, 3. And 5 is the greatest so far on 2, 1, 5. And 1 is not because of 2, 1, 1. Okay, so I think I understand what this question's asking. So I think what we do is just kind of, we could just do a DFS and keep track of the number of the biggest number we've seen so far on that path. So for instance, we could say if not root, return. Otherwise, we want to call good nodes. Yeah, that's fine. If good nodes, actually just good nodes dot left, or sorry, good nodes, and then we will pass root dot left, and good nodes, and we'll pass root dot right. So now if I were to print here, dot val, and I need to add self here. So I'm guessing this will give me a depth first search. So this will be root left right, which is pre-order traversal. Okay. I have to return an integer, of course, so I will return 0. And let me look at the output here. So 213115. Okay, as expected. And then if we look at this one here, it should be 1234 negative 1. Oh, it's a different tree from the example. Okay, so if I draw this one out, it's 3 3 0 4 2. So I'm expecting 3 3 4 2. 3 3 4 2. Okay, perfect. So basically, I think we also want. So let me just make a separate function here, which will take in root. And here we will call it again. Okay, so just to make sure that's working, I'm going to call it one more time. 213115. Okay. So what we also want to do is have like a like the highest that we've seen so far. So, and then what are the nodes able to be from negative 100 to, okay, so we'll call it with negative 101. So it always has to be greater. So what we want to say is if, so we'll say if highest, or we'll say this, if root.val is greater than highest, then we found a good node. So we will say print root.val. So f string root.val is a good node. And then what we want to send it, and then also what we want to say is highest equals root.val, and then we'll pass the new highest. And otherwise I'll just print root.val is not a good node. Okay, so let's try with this. So it is a good node, not a good node, is a good node, not a good node, not a good node, is a good node. And then for the other case, 3, so the good nodes here should be 3 and 4. So 3 is a good node, 4 is a good node. Okay, so this looks nice. So instead what I want to do now is have a count called numGood, which I'll set to 0. And then I can say numGood plus equals 1, and then I can return numGood like that. Okay. I don't know if there's a better way to do this, but I can say non-local numGood. Expected output for this one is 3. Oh, contains no nodes with a value greater than. So this is also good. So we just say greater than or equal to. And that should work. And then let's see where we get an error. Oh, that's it. Okay, so that's that one. Since that was only 7 minutes, I'm gonna do another one for this video. First time in history, we're gonna do double problem. So before we move on, essentially what you do, so if I were to clean up the solution a bit, get rid of the print statements and everything, yeah, you basically just you do a DFS and keep track of the highest that you've seen so far. I could see in the solution how they do the numGood, so I don't have to use non-local. Oh. Oh, so they just return it at the end there. Okay. Okay, cool. So we'll try this problem then. I haven't looked at it, but I have an idea of what it could be. So, all right, so that's that one. All right, valid binary search tree. Given the root of a binary tree, return true if it is a valid binary search tree, otherwise return false. A valid binary search tree satisfies the following constraints. The left subtree of every node contains only nodes with keys less than the node's key. The right subtree of every node contains only nodes with keys greater than the node's key, both the left and right subtrees. So I think for this one, what we can do is just kind of DFS through it and make sure that every tree is a binary. Or so we'll say that root.left is less than roots and root.right is greater than roots, and then we will say and that root.left is valid BST and root.right is valid BST. So if not root, we'll return. If we get to null, I think that means true, right? I'll just keep that there. Okay, so I'll make a Boolean called values, and this is equal to if root dot left. Actually, let's say, so basically if, and what about equal? Less than, greater than. Okay, so we'll say root dot left is less than root, which is, and then root is less than root dot right. So this will give us either true or false. And then, so I think we just want to return values and self dot is valid BST for root dot left, and self dot is valid BST for root dot right. So essentially that the values of this tree are in order, and that both the other one, like both subtrees, are also. And now with this part, so if we get to a null, so that should be true, right? And then if this is ever false, then we know that it's not. Oh, the values, of course. Okay, let's see. Yeah, so we can't check the... Okay, so let me just think of the base cases here. So if we have a tree that looks like this, let me just draw out a couple base cases. So case one, we could have a tree that has a value and both of these are none. We can have this. We can have this. We can have this. Okay, so okay. So this is, so I guess what we could say is if not root dot left values equals, I would consider this a binary search tree as long as roots dot val is less than root dot right dot val. But okay, so if they're both null, so we could say if not root dot left and not root dot right, then that means we should return true. If only not left, then it depends on these values, and conversely, if only, can we just say else? I don't know. If only root dot, so if only the right one is missing, then values should be, I don't think we need this, because we should never call, like root should never be null, I think. But let's take it a little slower here. Okay, so if root dot right is null, that means values equals if root dot val is greater than root dot left dot val, and we know this has to be a value or else it would have executed here instead. I'll just put these here even though we don't really need them. Okay, so if they're both null, left null, right null, and if they're both so else, so if they're both not null, then we just do that. Now, is it possible, for instance, all right, so if left is null, it will still call it here. So maybe what we could say is return values and self dot is valid bst root dot right. Maybe we don't. Yeah, I'll just keep it like this for now. And then here, and if the left is valid, and then here would be like that. And if they're both null, then it's just true. Yeah, because that means it's a leaf. So if we get to a leaf, that's a valid binary search tree. Okay. So let's try that. It seems to work. Okay, here we have a example that failed, so let's look at it. 5, 4, 6. Null, null, 3, 7. Okay, so first we'll look at this tree. It is both non-null, so values should pass. And this one also passes. And this one should also pass. So why is that false? Oh, because 3. Oh, I see. So 3. Okay, so 3 is. So 3 is greater than 5. So therefore, this is not a valid binary search tree. So you have to actually look. So essentially, all of these. Okay, I think I have another way of doing it. So in this case, if I undo all my marks, so everything here has to be less than 5. Everything here has to be greater than 5. Everything here has to be greater than 6, and everything here has to be less than 6, but greater than 5. So I think what we want maybe for every tree is like a min value and a max value. So I have DFS roots, min val, max val. So it has to be like in between those. I think we could just say if not root, return true. Whoops, return true. Because if we get here, that would be true. Okay, so initially we'll call it with the roots, the min val. So it must be, so min val is like the I'll just say floor and ceiling. So the floor, it has to be above. So the root to be valid has to be above negative 1001 and below 1001. Okay. So we want to check. Okay, so if we have a tree, we want to check, is this. Okay, so in range, I'll call it, is a Boolean, which checks if the floor is less than root.val and root.val is less than ceiling. Okay, so and then what we do is basically pass this. So we'd say DFS of roots dot left root dot right. No. So root dot left. So if we're searching on the left side of the tree, then this has a ceiling of 5 now. So it can't go above 5. So we'd say floor and root dot val. And this one, root dot right. So on the right, the floor goes up to root dot val, and the ceiling remains the same. So I guess we'd want to return the in range and both of those. Let me comment that out. Oh, I need this. Okay, let me try this. Your output was none. I should probably return that. Okay. All right, awesome. I'll just condense this a little bit. So if it's in range and left BSD and right BSD. Oops. And then I might not even, no, I do need this. Okay. Great. Okay, so this looks good. So we have to check the 3 conditions. I think this in range, like the value has to be between the floor and ceiling is a good way to put it. And also instead of doing all those edge cases, I think if you just say that this one is true, it simplifies a lot of the problem. Because if you get here, then that's good. So we can fail pretty much only if in range is false, which is what we want. Okay, so there you go. First ever 2 problems in one video. So this was day 18. We did count good nodes in binary tree, which basically we just had to say, is this node the largest that we've seen so far on the path or equal to the largest? And this just validates a binary search tree. So that is everything. So I'm guessing it was... All right. Great. So that's everything. Thanks for watching, and I'll see you tomorrow for day 19.